So here we're looking at current, potential difference and electromotive force. What we need to think about is the fact that inside an electrical wire, the electrons are already there. So if we imagine we could see inside the wire, the electrons are there in some kind of way. Now, not all of the electrons are going to move because, of course, some of them are bound to the protons. But what we have is something that is a good conductor. It's got lots of conduction electrons. We could also say delocalized electrons as well. That just means that they're free to move. Say delocalized also. So we've got the wire and the electrons are there. But nothing really very much is going to happen. Nothing very interesting to us right now is going to happen until we start to give them some energy. That is what we term as EMF. That's the electromotive force. Now, slightly confusingly, it is not a force, but it does make stuff happen. So it's where this idea of force kind of gets mixed into it as well. Okay, doesn't get measured in newtons, so it is not called a force. It is measured in volts. So of course we need to find some way to give it voltage. So we could do it using a cell, or of course two cells linked together. We call it battery. There's obviously lots of other ways of doing that. You could have a generator which does create electromotive force as well. But we'll just think about this to begin with. Let's just say that we've got two 6 volts, so we've got a 12 volt supply up here. Now again, nothing's going to happen. The EMF is there, all right, and we could measure that with a voltmeter. And yep, we would see 12 volts. Remembering that a voltmeter needs to be connected in parallel, that is on either side of a component, because it's measuring a certain difference. Anyway, we've got this EMF up here, and to make stuff happen, obviously we want to connect it in a circuit. So we might have a switch here, and then we'll just make a simple series circuit here with 2 bulbs. And there is our circuit. And of course, again, nothing is going to happen because the circuit is not yet complete. What could happen as well is we could measure the potential difference across this. Now, even though nothing's happening, we're still going to get 12 volts across this because it's very much the same as connecting it to here and to here. We're just doing it at a slightly different place. But we switch the circuit on. And what we're going to get is we've got the EMF, that's the electrical energy going in. And what we also have is the potential difference. And that is essentially, that's the energy coming out. And that's because these components have resistance. So certain amount of work has to be done pushing the charges through these things here. This brings us then a bit closer to a more refined definition of voltage because, okay, we've got the electromotive force, which is in volts, but we've also got the potential difference in volts. And that brings us then, we can get to a definition of this, that they are both defined as, so we could define the volt as the energy per unit charge. So the charge is the electrons are being pushed around, and it tells us how much energy is being carried by each unit of charge. Now, the reason we talk about unit of charge is because electrons are so ridiculously small that instead of thinking about each individual electron, we think about merely a big quantity of those, which is the coulomb. So we've got these coulombs, so like big bunches of charge, many, many billions and trillions of electrons moving around, and that big bunch might be carrying, let's say, 1 joule, in which case we've got 1 volt because it's 1 joule per 1 coulomb. But in this case, each coulomb is getting 12 joules. So then we can maybe get to more practical use for coulombs. Now, if they're moving, then what we have is an electric current. So if the charges are moving because of this, because there's some source of EMF and it's connected in a circuit, then we're going to get an electric current. So we get to our definition of current is the amount of charge passed per unit time. So I equals Q over T. You'll often see that just written as Q equals I times T. So that's the total amount of charge passing is the current multiplied by the amount of time. So that brings us to those, and we can see that these things kind of come together a little bit as well, because if we have more volts, that means each charge gets more energy. Quick moment here while I check the syllabus that I've actually talked about everything I need to for this. Oh yes, and also our meters. So of course we've got our voltmeters connected like this. Oh yes, what I wanted to say was, okay, if these two bulbs are identical, so we've got a voltmeter connected across here. We see that 12 joules per every coulomb is given, and this is 12 joules removed for every coulomb, so all the energy goes out. Doesn't quite all go out, of course, because they need some energy to get back all around here, but we kind of ignore the resistance of the wires because it's so small that it's fairly insignificant. What we could also have is we might decide to connect a couple more voltmeters. Now, as I said, these two bulbs are identical. So that means that each is going to transfer out the same amount of energy. So here we have 6 volts, and here we also have 6 volts. What we could also have is another meter we could connect, which let's say we connect it in here like this. So we put it in right there. There's your ammeter, which is measuring the electric current. Now, the electrons don't get lost, and you remember that current is charge divided by time, so it's how quickly those charges are moving through. So at all points around this loop, that current should measure the same.